But what does hyperscale mean? Like, it's usually when you have a certain level of complexity that you need to tackle. And so, yeah, let's go into this a little bit. So before we get into it, I just want to talk a little about who I am. I've been doing big data for a while, worked at Facebook for a while, working in notifications. And we're going to talk a little bit there because one of the things about notifications and hyperscale is Facebook sends like sends like billions of notifications every single day. So I definitely bumped into some scale problems there at Facebook. And then in data security at Netflix, I worked there. The main pipeline there that I bumped into scale is the network log pipeline. So I was a big contributor on the networking. So it's the pipeline that processes every single network request that Netflix receives. That's the biggest scale pipeline I ever worked on in my whole career. And then more here at Airbnb. The main one that I bumped into a lot of scale at Airbnb is around the profitability pipeline that I work on. And that one is different. It's not scale in terms of like volume or velocity, but it's scale in terms of variety, because that pipeline is just so complicated. So yeah, some other things about me. I'm a creator on LinkedIn. That's my biggest platform. Talk about big data stuff every day. So if you want to follow me there, that'd be great. So yeah, let's hop into it. Okay, so big data and scale, right? There's a couple different things that you want to think about with scale. And like, I really like the paradigm of like the 3 V's of big data, where you have volume, you have velocity, and you have variety. And solving the scale problems for each one of those is somewhat different. And I bumped into some serious scale problems in each one of those buckets, and we're gonna be going over this today. So why is dealing with scale challenging? So let's just talk about that for a second. So for example, the pipeline that I worked on at Netflix, like that was is over 100 terabytes an hour of data. And so like, if that pipeline isn't optimized, it's going to cost millions of dollars, right? And if you can optimize it, you can save millions of dollars. So there's like one side of it that's challenging is just like the financial risk of the scale. Like mistakes or wins have like they're amplified when you're at hyperscale. Some other things that are interesting about scale that are challenging is like, for example, if you're processing 100 terabytes, right, then it's like that might take a while, right? There's like the dev cycles are usually a little bit longer. And so you have to be a little bit more careful and really think through how you're going to solve this problem. I definitely noticed that. I think another thing to think about with scale that a lot of people don't consider, and this is more from the kind of variety angle of scale, is dealing with scale when it's variety is also dealing with a lot of people, right? And managing all those relationships and understanding like how to get your upstreams to commit to becoming high quality so that you don't have to suffer as much. And so you can have a lot of like people problems actually at scale as well, which is different than like the standard things that when you think of like distributed compute, more computers, like more memory, or like how to kind of handle those other things, right? So yeah, those are the main challenges that we kind of talk about here with scale. And yeah, let's kind of dive into some maybe a little bit more like concrete examples here. Okay, so hyperscale, right? A couple slides back, I was talking, right? We have 3 main ways that scale can be you can bump into things, right? You have that volume, variety, and velocity, and those are the 3 ways that you can, as a data engineer, you can really land a lot of impact, right? Because if you optimize a high volume pipeline, you're going to save a lot of money, right? If you optimize a high variety pipeline, you're going to save a lot of time, right? Because a lot of times high variety pipelines have a lot of data quality problems, and they have a lot of like integrity problems or SLA problems because there's just so many sources and one of them is bound to be late, right? So if you can optimize a variety problem, then that is going to save a lot of engineer time, which is very precious. And that's like, if you can save time, that's one of the most important things. The cool thing about velocity problems that I think is interesting is that like, if you can solve a velocity problem in a very optimized way, it's more than just saving cost. You can also unlock new capabilities, right? So if you have a real-time pipeline and you're trying to detect like a security threat, If it's not in real time, if you do your security threat detection on a daily basis, it's worthless. But if you can do it in real time, then you can actually respond to a threat when it's detected, right? So you actually unlock new capabilities if you can handle the scale problems of the velocity side of big data. It's interesting though, because I think velocity is also one where there's this other side to it where people like data scientists and data analysts and people like that, they want their data as quickly as possible, right? And a lot of times that makes data engineers think that they need to go to streaming. But streaming can be complicated, and streaming, especially like if you already own a bunch of batch pipelines, if your team already owns a bunch of batch pipelines and you're trying to branch into streaming, one of the things I've noticed over my career is like teams should either focus on streaming or focus on batch. If you have a team that's split across streaming and batch, that can make on-call a lot more horrendous because like the batch pipeline and a streaming pipeline, like troubleshooting those, very different, right? And they're very different paradigms. So like when a lot of your stakeholders are asking about velocity, you want to make sure that you understand what is the capability that is unlocked by having it be lower latency. And if the answer to that is that the data analysts can run their query faster on more up-to-date data, that's probably not a good enough reason. That's like, generally speaking, when that has been the ask, like I've always pushed back on that. It needs to usually be like, if like you have something processing in real time and it detects stuff in real time, and then it does an automated action in real time. And then that is the kind of amazing, like almost superpower that you can get from data engineering that you can't really get from the volume or variety buckets, but that like you get if you find the right problem. But those problems are actually pretty rare. Like I would say that those problems are like 5% of all data engineering problems. So I keep that in mind as we kind of go through the rest of this presentation. All right. I'm going to start here with volume. Volume is the one that, you know, when people think of big, they really think of like space, and they think of like terabytes and petabytes and exabytes and all that, right? All those numbers in the cloud, all those ones and zeros, right? And so, yeah, let's go into this a little bit. So really, when dealing with hyperscale, there's going to be two kind of like tenets, right? One is going to be like shuffle is your enemy. So if say you're processing 100 terabytes and you're trying to join it with some other data set that's pretty large, like a data set that's so large that it can't be broadcast, that's going to be a very, very, very expensive thing, because shuffling 100 terabytes of data is going to be essentially a showstopper. Like you can't do it. Like that's like, or if you do it, like Jeff Bezos is going to get very, very rich, and then like, and then your company is not going to make any money. So you want to avoid shuffle. And how do you avoid shuffle, right? So one way is if you're doing a join on the data set, that join needs to be small, right? That data set needs to be like under 10 gigs, right? So that you can broadcast it. Because with Spark, right, you can change the broadcast threshold, and you can actually broadcast bigger data sets. You have to allocate more memory to your executors and all that stuff to make it work. But you can actually do that, and that can remove shuffle, and that can make it so that the job runs a lot faster. Or another thing you can do is that like you can fix this at a different layer. So like maybe instead of doing a join, you like when the data is logged, you just log the field that you need, so that like every time you have a log, then the data is already there, and you don't need to do a join, and then you can just like do an aggregation or whatever that you need. And then that's going to be a lot better, because those especially shuffles that are caused by joins in big, when you have very high volume, that's going to be very painful and very expensive. Another thing to think about here is smaller batches may be your friend. So what I mean by why is there the word may there, right? So for example, like when I was working at Netflix and working on that pipeline that was 100 terabytes an hour, it's easier to solve that problem at the 100 terabytes an hour scale than it is at the 2 petabytes a day scale. Because imagine trying to write a pipeline that like you're just going to read in 2 petabytes, right? That's just like a lot of data, right? And like trying to solve the complexity when it's that high is like, it's not going to work, right? Your job's going to be really, really slow, or it's going to be very unreliable, or whatever. And then, so you want to batch it up, right? And you want to like maybe think about things on the hourly scale. I generally don't recommend thinking about things like lower than that, like on like the sub hour, like the every 15 minutes or 30 minutes scale. Main reason for that is because Spark and these like big data processing tools, they have a startup cost, right? Because it's like when you run a Spark job, just to kick it off and get it to run, right? It takes like usually at least like 2 minutes just to get the job running, right? And so like if you're running the job every 15 minutes, that 2-minute startup cost is actually starts to be a larger percentage of the window. And it makes it so that like the jobs can't finish in time. And so that's where an hour is usually nice. It's like a good middle ground. But it's the reason why it's smaller batches may be your friend is that there's a chance that you're not processing like fact data here. You're not processing logs. Maybe you're processing dimensions, right? And then in that case, you might not want to update all of your dimensions every hour because maybe only a small percentage of them changed. So in that case, a lot of times you want to work still at the daily level and just kind of figure out a way to get your dimensions to update once a day, because otherwise like updating them 24 times a day when most of them haven't changed, that is going to be very expensive and probably not going to solve your problem. But for fact data and log data and event data, smaller batches are always going to be your friend. And those are going to be really, really powerful. Okay, so now we're going to talk a little bit about this, like on like just a little bit more of a concrete example of something I worked on with a couple of my other coworkers at Netflix. You'll see there's a link here if you want to like check it out yourself as well, get a little bit more information. So essentially what we wanted to do here is we need to figure out, so when we get a network request, we need, so Netflix, right, they have a microservice architecture. So what that means is there's not just one app in Netflix, there's like thousands and thousands of apps. And so, but we like when a network request comes into the VPC, we don't know which app it's associated with. And so what we need to do is take the IP addresses that map from IP to application. So then we can see like, okay, this request went to this app, and then maybe this app talked to this app. So then we can kind of see like how our microservices are talking to one another. And so a big thing that we want to do there is get this, and you'll see down here this mouthful SQSQ, this Apache Spark step down here. That is where you're going to join the IP data. And that data was small enough, right, that we could get it down to being a broadcast join so that we don't shuffle. Because if you do shuffle here, that is going to make this a lot more challenging. One of the things that's interesting about this problem, though, is that like we found an interesting kind of breaking point with this design is that like we were able to broadcast join IP data, but only if it's IPv4, right? Like the old IP address data, because that space is a lot smaller. IPv6 data is very, very large, very, very huge, right? And it would be impossible to broadcast the entire IPv6 data set into here. That would have to happen over shuffle. And we tried that, and obviously it doesn't work. Data's too big. So in order to solve the problem at a different layer there, right, what we did instead here is going forward, what you do is you log the app. So when in this flow log file, you just, when the event is logged, we have this thing called a sidecar proxy. And the sidecar proxy enriches the request with the application name. And then we log it, right? And then that just removes the need for this join. You don't need it at all, right? And then this problem becomes dramatically simpler, and you don't have to like even like you're essentially at that point, once it's logged, then your logs are already the data. You don't even have to do any processing on them, right? They're just ready to go. You just need to aggregate them to see like which apps are talking to which apps. But that's going to be a cheap aggregation, right? Because that's just a group by, and the cardinality there is only like a couple thousand. So that'll be a pretty cheap group by to do. So yeah, that like I highly recommend reading up on this link here about this design on like how to handle this data set. This is like very large volume, as big a scale as you could imagine. It's freaking awesome. Cool. So that's kind of like what I want to talk about with volume. I think there's I guess there's a couple other things that I think are important to talk about here, where, okay, what if you're in a situation where you need to do a join, that join can't be broadcasted, and you can't log the data, like you can't put the data you need in the logs, right? Because that can happen too, right? That you can have a design where that is the situation. So in that situation, you are going to want to leverage bucketing. So you can do this thing called a bucket join. So where you bucket both tables on an ID, right? Whatever your join key is. So then when you join that, it still does shuffle, but it doesn't shuffle the entire data set. It only shuffles within each bucket, which can dramatically reduce the amount of shuffling that occurs. And that is obviously it's not free to put it into buckets, but it's usually pretty cheap to do that. And then that can be a way to help minimize shuffle if you have to join like a large data set to your like hyperscale data set. That's the way that you're going to want to do that. There's another one that's similar to that. It's called an SMB join, which is a sorted merge bucket join. That's very popular, especially in Hive. And you can do it in Spark as well. And that's another way to do these joins without, and if you do a sorted merge bucket join, then you actually have no shuffle at all. It just does everything on the map side, and you don't have any reduced step at all. And so, but obviously, like having to sort all the data is expensive, and that is a shuffle in and of itself, right? So that might not be the best case, right? Because you do have to pay that cost somewhere. Cool. So yeah, those are kind of all the ways that I've thought about dealing with volume. I've worked, I've solved these similar problems at Facebook, kind of like with those kind of techniques, the bucket join and sorted merge bucket join. And so those work pretty well as well. I personally like this kind of design that we did at Netflix, where like we got rid of the join completely. It felt like some magic, right? It felt like, wow, this problem just disappeared. Okay, cool. Let's go to the next slide here. All right, now let's talk about velocity. Velocity is a good one because this one is kind of more, like hype right now, and everyone's talking about like, oh, we need our real-time data. Real data engineers use real-time data or whatever, right? Cool. So let's just talk about the two. So each one of these topics, I have 2 points to talk about. So the first point with velocity is streaming works great when the window is smaller, and then microbatch works when the window is big, right? So what I mean by that is if you are doing a streaming pipeline that's doing like a join, right, or something like that, where you have logs and then you're adding more things to that log, but you're not aggregating it, you're not holding on to data, or if you're doing like small sessions, maybe you're doing like a 15-minute session per user, or like some sort of like smaller window for sessions, then you're probably going to be fine. And that's how you can kind of aggregate and dedupe in a smaller window. Streaming kind of falls apart if you're trying to dedupe across an entire day, because then you have to hold on to every record for the whole day, and you have to hold on to all that in memory. And then like the amount of memory that you have is insane. And then you're holding on to like terabytes and terabytes of data just to dedupe everything. So I've even noticed that like when I was working at Facebook, I tried to use the streaming pipelines to dedupe notifications, right? And like it just OOM'd, right? It would run for like 40 minutes, and then it would just OOM. And then like I like talked with the info team, and I'm like, I need more memory. And then they gave me 10 times more memory, right? And then it ran for 4 hours, and then it would OOM. And I was like, okay, I need more memory. And then like the infrastructure team was like, no, you don't. You need a different approach. You need to do something different. And so that's where the second bullet point is really awesome, where you have micro batch works when the window is big, right? So if you need to reduce the latency, not to real time, right? Because real time is like a lot, but like if you say you need to reduce your latency a lot, especially on dedupe pipelines, then micro batch can be a really, really wonderful approach to doing that. And we're going to talk more about that in this next slide. Okay. So when I was like deduping notification events at Facebook, right? Initially, what we had was we had this one Hive job that just ran and it deduped all the events like in one query, right? One big old Hive query. That query ran in 15 hours, right? And one of the problems with that was that like this deduped notification events was upstream of a lot of other critical pipelines at Facebook. And so since there was a 15-hour latency, that mean that all these other critical pipelines could only start after 15 hours, which was like very painful for them. They made it a lot harder for them to iterate quickly. And so what we did was like we tried the streaming approach, where instead of doing one big query at the end of the day, we try to hold on to all of it in a stream. Doesn't work. Like, I mean, or it probably would have worked, but like the amount of like memory and like RAM that we would need would have been like prohibitively expensive. So what we did instead is we do hourly deduping, right? So you'll see in this diagram here, we have like a big tree, right? So there's going to be a total of like 24 hours that you need to dedupe, right? So you can imagine what we do here is like we have a wait for hour one, and then we within the hour we do a group by of just that 1 hour of data, and then we do it again for hour two, and then we merge those two and do another dedupe between hours 1 and 2. And that's how. And so here, once we're at this merge step, we have deduped stuff for the first 2 hours, right? And then the cool thing about this is this can run while the data is being collected, right? So hour one can run like immediately after 1 hour has passed, right? And so it can start running 23 hours sooner than if you wait till the end of the day, right? So that's really powerful. And so if you use this kind of tree merge concept, where like then after you merge hours 1 and 2, 3 and 4 like this, and then you merge those together, and then you merge those together, and you merge those together, and then finally you get this final merge here. And this step actually runs really quickly. So this final merge, this last step runs at the same time that the old query started at, but this step runs in like an hour instead of 15 hours, because all the deduping has mostly already happened, right? And we've already gotten rid of all the dupes from all these other steps. So so instead of taking 15 hours and waiting, then people were able to have all their deduped notification events in like an hour or 2 hours after the next day. So, and people are very happy with that, because then this job was a lot more reliable, and it really enhanced a lot of other people's downstream jobs, and they could run a lot sooner. I have a GitHub repo that you can check out. This link, there's an Airflow repository, or I have an Airflow example of like how to structure a DAG like this, because I'm sure one of the things you're looking at, you're like, this DAG has a lot of steps, right? This DAG has like, there's a lot going on here. So definitely check out that link to kind of dive a little bit deeper here than what I've done in this presentation. So the reason why this worked, right, is that like we never really are dealing with a ton of data until the final merge down here. And at that point, it's already sorted, it's already deduped, and it's already really fast. So in that way, this micro batch solution was more robust than a streaming solution, and it solved the problem in a way that was good enough to solve what they were looking for. That being said, right, if you have streaming jobs that don't do dedupe, and all they're doing is like going to a fact table, or it's just like a simple read, and you're taking data from Kafka to Hive, or like it's like a simple transform, streaming is so good for that, because then you don't have to hold on to any records at all, and the memory that your streaming job needs is actually tiny. And so that's where streaming jobs can be very, very robust. But once you introduce like dedupe or group by or join can be okay as well if the join is like kind of small. But like especially dedupe and group by, those make streaming jobs need more memory, and at hyperscale it just doesn't work, essentially. And so and that's where you need to think about things in a different pattern. And this is like, I really like this pattern, because this micro batch pattern, because it's a nice middle ground between like running things daily versus running things in real time, right? And you can still get reduced latency, but without the penalty of like having to set up a streaming job when like you might not know streaming jobs. So definitely check this out for sure. Velocity stuff is really cool. All right. Now we're going to go to the third one. This is the section that like I've done this pattern a lot, and variety patterns are really sick. So what do I mean by variety here? So some data pipelines rely on a large number of sources, right? So for example, at Airbnb, we have this unit economics pipeline that computes whether or not a reservation was profitable. And you can think of like all the things there, like, did they use a coupon? Did they file a claim? Which credit card did they use? Was it Visa or Discover? Because those charge differently, right? And it's like, okay, what country were they in? Because the tax rate is different depending on the country, right? And so there's like tons and tons of things that go into that. And then you have to read all of those sources together, get them into one schema, just so you can get that final like profitability number, right? And I've done this pattern a couple times, this variety pattern. I've done this once at Netflix and once at Airbnb for products that were really, really powerful. So yeah, we're going to talk a little bit about a design here. So variety, right? There's going to be two things here. So you need to standardize the schema, the ETL, and the data quality. That is an important part. And the second part, which is more soft skill oriented, is you need to work with your upstream teams to reduce landing times. So your upstream data sets should be as optimized, or your upstream sources should be as optimized as possible. Sometimes it's easy because like your upstream source is like a REST API. And so you're just hitting live data. And so those guys don't need to do anything. But if your upstream source is like a data table, maybe that data table is like really terrible. Maybe that data table is created by some 1,700 line SQL query that makes your eyes bleed. And you don't want that. Right. And so you need to go work with them and be like, hey, make your SQL better because it's bad. Right. And having those conversations can be really helpful, and they'll really help reduce the pain that you'll experience. Because a lot of time, if you own these data sets, these downstream data sets that depend on 40 or 50 upstream sources, like almost once a week, someone's gonna be like, hey, your data's delayed. And then like, you're like, yep, it's delayed. And then you're like, okay, why is it delayed? And it's like, oh, it's that same stupid table that's always delayed. And then you have to go talk to those guys and be like, hey, unblock your table. And then they'll unblock their table. And then like, after you have that conversation once a week for a year, you're going to go insane. And then you just need to talk with people, right? And actually like get them to solve the problem in a more robust way, so that you don't, just to protect your mental health and your own sanity, right? So yeah, let's go to the next slide here. So this pattern here I've created, it's an interesting one. And I have a GitHub repo here. So this pattern I call the little book of pipelines. And this is essentially a way of handling an arbitrary amount of variety in a scalable way. So the way the little book of pipelines works is, the first thing you need to do is you need to define your schema. And this is the schema that all of your sources and all of your upstream and all of your jobs, they need to push all of the data into this schema. In this case, we have identifier, which is what things are usually deduped on, type name, right? Like when I was working at Netflix, I built this, and it was a big pipeline to collect all of the different objects in the infrastructure. So in that case, it might be like an application or a database or a load balancer, right? And then properties, this is like a flexible map of like whatever other properties you want to put in this data set. And then group name is the partition key, right? So this is how you're going to partition your table for each one of these individual jobs. All right. So we'll go, make sure to look at this link though. A lot of this stuff is a lot more spelled out there. So the next step after you create this schema is you need to create these enums. So in this case, we have, and these enums are called an item group. So an item group is a collection of items, right? So in this case, we have group one. And so name group one. So this group one here is the same as the group name here. So that would be the partition key, is this name here. And then you have items. So this is the list of all the items that you were expecting from this group. Sometimes there's only gonna be one, or it could be n number of items. And then inside the item schema, right, you have an item name, right? In this case, that might be like application, load balancer, or like whatever other item name you want. It's very abstract, right? So it can kind of handle a lot of different cases. Then you have your data quality thresholds. So these things are going to be how you can standardize your data quality. and you put your data quality thresholds in Scala, and you don't put them in Python or in Airflow, right? Which is, I like that, because then like all your data code and all of the configuration and everything is just in one spot. And then the last thing is item level properties. So this is just things that are like constants that are connected to this item. I just put an empty map here. You could have a bunch of different things there depending on how your items, if they have any sort of constant fields that you want. I highly recommend checking out that stuff. So after you define your schema and you define your enum, then what you need to do is you need to define your base job. So your base job takes in two things, right? It takes in a group, right? So in this case, it could be like group 1, group 2, whatever, right? And then it takes in a source, right? And a source here is a function that takes in a Spark. So it takes in a Spark session and it returns a data set of intermediate data set. An intermediate data set, remember, that is this schema back here. So when you define this function, right? So this is our abstract job. So keep in mind, this job does not like actually run. We have to implement this job in various other forms, right? So then what you have, right, is you have this output data table. So this schema sum output table, everything's going to dump. That table, this sum output table should have the same schema as intermediate data set. They should have the same schema, right? And then how it works is it's pretty simple, right? You have Spark, you build your Spark session, and then you get your data frame by calling that source function. You pass Spark to the source function, and then you write the data frame out to the output data table. That's pretty much it. Pretty straightforward. So now I want to show you what a job looks like an actual implemented job. So now we're in the object case. So now this is a job that can actually be ran because this is a concrete implementation. So in this case, we have a job, right? And we specify the group. The group here is group 1. And then we have our source, which then creates a data frame that reads from an input table. And then it adds the identifier, type name, properties, and group name columns. And then it casts it as an intermediate data set. So then it's returning the right value. And then this job will run, right? And this job will, so then all you got to do is, as you get more groups in your data pipeline, right? There might be 7 or 10 groups. You create more jobs like this, and then each job will output to that same intermediate data set schema. And then that is how you can kind of consolidate everything. And the cool thing is so the last kind of piece that you want to include here is, if you go back to this item group enum, you should also have a job. And what the job does is it takes this enum and actually turns it into a data table, right? Where it's kind of a data table where it's like you have group 1, and then it flattens this list here of all the items. And then it has like group 1, item 1, and then all of this as like columns. It's a very small table. Usually it's like, depending on how many groups and items you have, it's probably going to have like 20 or 30 rows, right? And that little table is what this design is very powerful about, because then you have the data quality thresholds. You can access them in Airflow by joining, right? So you don't have to configure them in Airflow. You configure them in Scala, and then you access them from joining, right? And that's where the name comes from. The little book of pipelines is, you have these groups that all define like a specific pipeline, and then those each group maps to a specific implementation job. And then that group then has its own data quality parameters. And that is how you can kind of have standardized data quality across all of these, and a very concise API. So conclusions here, right? So volume, right? 2 things to remember: minimize shuffle with broadcast joins, maybe bucket joins. And the other thing is like, if you're doing fact or log data, then use smaller batches, hourly windows, right? Velocity is the big thing there, is like streaming for small windows, and then use micro batch to reduce latency otherwise, if you are trying to do like a daily dedupe or something like that. And then variety, right? The 3 big things here: standardize your schemas, standardize your ETLs, standardize your data quality checks, and do this all with an enum, right? And then that enum can then be turned into a table, and that table can also be used in dashboards and all these other places. Like it's a very powerful little table that describes your whole data ingest. So yeah, that's pretty much it. I think I have a couple questions, a couple minutes for Q&A here.
Yeah, you do. And there's a there's a few questions, but first off, thank you so much for all of that. Definitely a bunch of just. I love how in depth you went into the V's. I think that's what I was like. Oh, this is very well broken out. I feel like everyone kind of just high levels it, but it's nice to like kind of go deep down into each.
Oh yeah, for sure. Go deep there. Yeah. So what kind of questions do we got?
Let's see. Book recommendations for engineering at the hyperscale. If they've already read designing data intensive applications, but want something practical. Any thoughts?
I mean, I like Joe Reese's book. Like that, like his book is like it doesn't have quite as much of the hyperscale stuff in there, but it like if you get these fundamentals, like a lot of that stuff, a lot of the stuff I talked about today, like is just an extension of fundamentals of data engineering anyways. So if you have a good grasp of distributed compute, the conclusions that I came to in this presentation are pretty straightforward. So definitely check out that book. I like that book a lot.
Yeah. I just missed the other question. Oh, here. What's the way to handle? I'm sorry, I'm covering your face. What's the way to handle operations? 100 gigs of like Spark data frame. It does have if it does have shuffling involved. Can't use broadcast.
Yeah, 100 gigs is usually going to be fine. Like, I mean, you're going to like that the scale, most of the stuff that I'm talking about here, you need to have another couple zeros there. Like, like I would say that like really you're going to really bump into a lot of problems here when you're at like 10. If you're at like 10 terabytes, that's when you're going to really have some problems here. Like 100 gigs should be fine. Like, yeah. I mean, if you're having a problem there, that might be something with like EMR where you're not getting enough resources or something like that. If it's really slow, it could be actually like a platform problem where you actually need to get more compute and more resources. It could be that, or like you could have like you might have like some join logic that's messed up. That's like doing like a cross join or like some other thing there that's making it slow.
Yeah.
But generally speaking, 100 gigs, like that should be, Spark should be able to crush that. So yeah.
This is I do think that should be very true in terms of like that size. I actually when you brought up network, I think I ended up interviewing for that team as well, like the infrastructure team for being a data engineer, and like a lot of their questions were around like no, but like how would you handle this like massive amount of data? It's like I remember there's like one thing about like analytics where it was like, okay, how would you store all of this? And like you have to like aggregate it, and then how would you like reverse find the average because you don't want to store all of this data like as a single row. It's like what if you just store it all as like a aggregated row instead? So it's very very different setting.
It's crazy how different data engineering roles can be and like what you have to focus on. Whereas like in these other roles, like you can have other data engineering roles that are like hyper focused on the business, right? But then you have these pipelines where you have to hyper focus on like the technicals because they're just so large and they just like slap you in the face, right?
Yeah, for sure. Yes, they do slap you in the face. No, I remember like I was like our quotas was like maybe in the terabyte, and then like you'd go over to like the ads team and it's like petabytes. Like we're dealing with petabytes here. This is very different scale. So just one question in terms of, I think maybe you're maybe data-driven kind of design there in terms of the mapping. So maybe just why not put it in Scala? If that's, or maybe you run it through Scala. I imagine you're just running it through Scala.
We're talking about in the volume here, or like which design are we talking about here?
I'm assuming this is, so why put that into Scala instead of having that be data-driven? You know what? I think
that's a great question. So, why put it in Scala instead of having it be like in the DAGs, right, with Python, right? Like, I think one of the reasons why I like to put it there is then all of your configuration is in one place. Because then like your data engineers, you can ramp them up on it a lot quicker because it's like it's just all in one spot. Right. As opposed to being like, oh, yeah, we do our things here. And like the other thing I don't like about the DAG place is like a lot of times like getting everything into that nice like enum structure. Because then if you don't put it in Scala and you put it over there, what you have to do is essentially create a copy of the enum in Python. Right. And okay, but initially that's what I did. I created a copy of it into Python, and I was like, wait a minute. This is kind of dumb. Like, why are we duplicating this same thing? And then like whenever I added a new enum to the list there, I had to like then pop it over into Python and like add it there as well. And I'm like, I don't like, I like having all of it kind of one spot. Like there's, I have some other like thoughts on like how to take that design a little bit further. That would, I'm gonna make a video on it or something at some point. But like that, like there's that one has, that design has a lot of legs to it for sure.
Yeah. I guess he meant more about the quality checks. Why not store them in a table?
You store the thresholds in a table and you run the quality checks in Python, right? And the way you access the thresholds for like percent non-zero, percent non-null, and stuff like that, you access those with a join. Right. It's a very easy, very lightweight join. That's an easy broadcast join. And so, yeah, you don't do the DQ in Spark, because like if you do the DQ in Spark, the problem is then you fail the job. And then like, what if it's a false positive, right? If it's a false, you fail the job on a false positive, and then you're like, I have to like reprocess everything. And it's like, super big pain. Right. And so like, yeah, it's because the Spark doesn't like putting the checks in Spark doesn't allow you that ability to be like, oh, it was, you know, it wasn't an issue, right? It was actually a false positive. So just skip this failure and go on. Right. So, and that's where it's better to have that be in like afterwards, right? After like when you do like write, audit, publish, right? So you write the data to like a staging table, and then audits. In that audit step, you should be using like probably like Presto or some other quick querying thing to then like check the staging data. And to get the thresholds, you join that staging data with this little book that I was talking about. And that's how you can get those thresholds that you're checking for, right? Like to make sure that everything passes. And so then, and then if those fail, then you can just, and it's a false positive, then you can just skip it, right? And it'll be fine. So yeah, that's like, yeah, it's definitely like one of the other parts about that design is that like, there's a lot of complexity in those pipelines, and no matter how you solve that problem, there is going to be complexity somewhere, and it's like annoying, right? Because the other option is you put those configurations and thresholds in the DAG, and then you just have this long list of configurations. And like, I personally was like, that's ugly, and I don't like that. So
no, that makes sense. All right, we're up at 3:30. I don't want to take more time than you've already given, and I really appreciate everything you've shared. So thank you so much, Zach, and hopefully we can talk again soon. Are you coming back to Denver?
At some point, yeah, for sure.
Perfect. All right, then see you then.